Masaki, yes, yes.
Please introduce yourself because I was not provided any information where you're from and your title, so your short bio or something like that.
Yes.
So feel free, like before your
Okay,
presentation,
okay.
introduce yourself.
Thank you, thank you.
Okay, go ahead.
Okay. Then, hi, I'm Masaki Nagai from Hiroshima University. So I'll start my presentation. The title is Effect of Processing Dynamic Characteristic Information of Tail-operated Hydraulic Excavator on Work Efficiency when switching to a different class. First is introduction. The Japanese construction industry has been struggling with a shrinking and aging workforce in recent years, and productivity per on-site worker needs to be increased. A tail-operated hydraulic excavator is currently being developed as a way to solve these problems. The tail-operated hydraulic excavator allows the operator to operate excavators from a remote location and reducing travel time and cost. Furthermore, work can be performed by switching to multiple hydraulic excavators in sequence, which is expected to increase productivity even more than operating an excavator on site. Considering such uses, there is a possibility that the operator switches to a different class of machines. The size of hydraulic excavators generally range from small class machine with a mass of less than 6 tons to large class machine with mass of 40 tons, and operators perform the work by building a class of machine suitable for the size of the site or the content of the work. And the dynamic characteristic of the hydraulic excavators also depends on the class due to difference in the weight of the machine and the actuators installed. And operators must perform operations according to the individual dynamic characteristics. And it is said that when operating tools or machines, people build an internal model of an object they are operating in the brains. When operating a hydraulic excavator, it is thought that the operator builds internal model in the mind for each different dynamic characteristic and switching between them each time and class changes. Quickly switching between internal model is also desirable for effective operation, but this requires a conscious understanding of the behavior of the object to be operated. However, tail-operated hydraulic excavator lack feedback to the operator compared with actual boarding. Consequently, the operator's machine without receiving sufficient information such as the size or posture of the machine, making it difficult to understand the machine's movements. And it has been shown that the switching of the internal model is not immediate if the understanding of the operation is lacking, and which may affect the work efficiency. Therefore, a method is needed to support the operator's internal model switching when the dynamic characteristic of a tail-operated hydraulic excavator change. Previous research has been investigated methods to support internal model switching, but to the best of knowledge, no methods to support internal model switching in tail-operated hydraulic excavators have been investigated so far. And therefore, the objective of this study is to propose an interface that supports the operator's internal model switching when the dynamic characteristics in a tail-operated hydraulic excavator change and verify its effects on work efficiency. Howard et al. Also argued that information that is more closely related to the motor task leads to greater effectiveness of contextual information in switching the internal model. An example of this is a change in proprioception, such as an amount of force applied or joint movements. Therefore, we propose a method to present the dynamic characteristics of the machine after switching after switching in advance to remind the operator of the change in the relationship between lever operation and movement as contextual information. A visual presentation was used as a method based on the idea that the operator can intuitively understand information about the machine's operation, such as dynamic characteristics. In this study, we focused on the swing operation. The video showed swing of the upper rotation body by step input. We also proposed displaying the control lever input so that operators can understand the machine's response to the lever movements. The words lever on were displayed at the bottom of the video. During the lever operation indicates that the input was in progress. We conducted experiments to verify the effectiveness of the proposed method. For experiments, a 30-ton class teleoperated hydraulic excavator was prepared. Here shows the teleoperated cockpit and hydraulic excavator used. The teleoperated cockpit consists of a monitor and operating lever. The teleoperated hydraulic excavator is also equipped with a camera that displays images from the operator's seat on the monitor. As for the dynamic characteristics, different dynamic characteristics A and B were obtained by changing the inertia of the upper rotation body, which was determined by the body posture and the engine speed. By switching dynamic characteristics A and B, it is possible to simulate switching between different classes. The dynamic characteristics of each are shown in the video here. This video was shown to the subject when switching dynamic characteristics. The experimental task was swing task in which a machine with a mark pasted on the front of the window made a swing of 800 degrees on the right from the initial state and stopped between the target. The target width was set to 10 degrees. 5 healthy adults with an average age of 30.8 years took part in the experiments. The experimental condition were switching with no presentation and switching after presentation. In addition, for each condition, cases were prepared in which the dynamic characteristics did not change or change from the middle for a total of 4 switching patterns. No switching and switching, respectively. The subjects performed a total 20 swing operations for each pattern. In switching, the subject performed the swing task with different dynamic characteristics between the first 10 times and the second 10 times. The data of the second 10 sessions were used for the comparison. The swing operation time was set as the evaluation item for the experiments. The change in dynamic characteristic could be said to have the effect if the difference could be confirmed by the comparison. And this is a result of the experiments. In switching with no presentation, the swing operation time of switching was confirmed to increase by 7% and 9% compared with that of no switching, and significant difference in dynamic characteristic B was confirmed by paired t-test. The significant level was set to 5%. Increased operation time means reduced work efficiency. In switching after presentation, no significant difference in the switching operation time was found, regardless of the presence or absence of change in dynamic characteristics. To assess the size of difference between switching and not switching, we also compare the effect size, which is an indicator of the size of the difference. As a result, we confirmed that the effect size was smaller with the proposed method compared to no presentation from 0.48 to 0.063 for dynamic characteristic A, and 0.621, 0.12 for dynamic characteristic B. Thus, the smaller effect size means that the proposed method was unable to suppress a reduction in work efficiency caused by switching. Here's the discussion. The figure shows the transition of swing operation time for each trial of dynamic characteristic B under each condition. The solid line represents no switching, and the dashed line represents switching. The data points are the average value of swing operation time for all subjects. The figure shows that the swing operation time increased in switching compared to that in not switching immediately after change the dynamic characteristics. On the other hand, with the proposed method, the swing operation time did not increase, and it is possible that the subjects were able to respond to the change in the dynamic characteristic immediately after switching. And this figure shows the average time series of the swing operation input for no switching and switching under each conditions. The average time series was calculated using dynamic time wrapping, a method for calculating the similarity of time series data, and DTW variance averaging, a method for calculating an average of multiple time series data. In addition, the examined value, maximum value for the operation input was set to 100. The figure shows that the maximum input was given during the swing acceleration operation, regardless whether there was a change in dynamic characteristics or not, and the input was decreased to perform deceleration operation after a certain point. However, on the left, it can be seen that it takes longer to perform the swing deceleration operation with switching compared to no switching. These results indicate that the subject needs the time to perform the swing deceleration operation due to the change in dynamic characteristics. The above result suggests that subjects in switching with no presentation were unable to switching internal model appropriately in response to changing dynamic characteristics and were unable to perform effective operations.
2 minutes to finish.
Finish? Okay.
2 minutes. You still have 2 minutes.
Okay. Meanwhile, no change in operation input were obtained in proposed method. This result supports our hypothesis that the proposed method effectively provides contextual information for internal model switching, and that this suppresses a decrease in work efficiency. Final conclusion. In this study, we proposed the dynamic characteristic presentation interface that support internal model switching in order to reduce the effect of change in the dynamic characteristic of a teleoperated hydraulic excavator on work efficiency. Experiments were conducted with a teleoperated hydraulic excavator to confirm the effectiveness of the proposed method. It was found that the swing operation time was prolonged when the dynamic characteristic changed without presentation. At the same time, no increase in swing operation time was observed with the proposed method, and the proposed method suppressed the effects to change in dynamic characteristics. In the future, we will examine the effect of switching between different classes on work efficiency and the effectiveness of the proposed methods. And that's all. Thank you for listening. If you have any questions, contact us, please. Okay, that's for finished. Thank you.
Let me do my job. So when, can you explain how your identification of your model was done? So you were using a camera. So per my understanding, yes, you recorded the movements from the starting point to the end point.
Yes.
Anything else you recorded?
No, I have just recorded the video, the movement of the excavator, and uh, then so I record the movement of the excavator and input of the lever operation, and in this.
What's the unit for this input?
Okay. And input is there is no.
Angle, like switching angle, or
You asking the input of the unit of the input.
okay. So that's probably the angle.
Okay. And angular velocity.
Yeah.
Swing angular velocity.
That's why you have command to certain angle, and now you're recording images in time. What was the frame per second for your recording the motion with your camera?
Sorry, could you repeat that again?
Yeah. What was the speed of recording the image?
Speeding.
Yeah, like how many frames per second you recorded during your experiment?
That that's speed.
Okay, and the last one. This dynamic characteristic, how you will call it? Is it like stiffness or damping? Is it a second order dynamic system, or is it first order dynamic system? Because you do not have overshoot.
Yes.
Because basically what you're doing, it's a step response function, right?
Yes. We use actual excavator to for experiment, and excavator have a non-linear dynamics, so we can't determine first or second dynamic. Yes.
Thank you very much again. Let's just give a little.
Thank you for listening.
Presenter, thank you very much. It was really interesting. So our second presenter is no first name. Sorry. Yeah. Is okay? You have your presentation uploaded, right? So please introduce yourself, your graduate student. Okay. Don't be shy.
Okay. Next. Okay. Hi. A little before. Okay. So hi, I'm David. I'm 15 years old. I'm a high school student, and I'm a student at the Associatic for of the Informatic Association of the Informatic for the Future.
So you're local. You're from Malaysia?
No, I'm from Romania.
From Romania. Okay. Go ahead.
Oh, okay. So it started.
Oh, Constanta, Romania.
Okay, so hello guys. Today I'm going to present to you boosting cognitive focus via binary search of attention types using brain computing interfaces. First, we will be starting with the content. We'll first start and talk about the introduction, why we choose to present this topic. After the materials, how it was done, everything. Thirdly, the methodology, basically how we put our experiments, what results we've obtained, and later on we will have a discussion about your questions. So let's get right through it. We'll be starting with the motivation. So in recent years, there have been a big problem with the attention span decline. So as you can see here from a diagram made by Gloria Mark, the attention span from 24 has drastically fallen till now 2024. As you can see, there has been an 150 in 24, and now just 40%. decrease bigger than 50%, which is a lot. So we've implemented a brain computing interface approach to solve this problem. How did we do that? Well, firstly, the study aims to help people train on educational materials in a way that they will be able to improve their concentration index through neuroplasticity. So basically, we're putting them into an augmented reality environment, recording their data live while they are looking at the educational materials and predicting their concentration state and their concentration index. As you can see here, I've made a little diagram to help you better understand our concept. So we have firstly the start screen. Here you can go to the learning process. There will be an educational material shown. The data will be lively pre-processed, feature extracted, classified with the ML model. If it is an effective type concentration, it will still keep adjusting the environment parameters. If not, it will offer visual and auditory stimuli such that the people will regain its focus. Next, we have the start screen. So you have two options to see your stats, like how much it has been increased for you to, how much your concentration has been improved. Next, we have Brainda, your virtual assistant. He will be helping you throughout your journey to improve your concentration. Next, we have the participants. So for this study, we've used 10 participants, 5 male and 5 females, aged between 8 and 17. It's pretty obvious, I think, why we choose this age, like 12 to 17, because it's the generation that back there has the biggest decline. Okay. After, we would like to specify that some of the subjects had some eyesight problems, but this isn't so relevant for our study. Next, we've used the Brain Access Media headset from Brain Access. It has 60 channels based on the 1010 system, 250 Hz sampling frequency. And we've also used the VR headset MetaQuest 3 to immerse people in virtual and augmented reality. Next one, we've trained some machine learning models to determine their concentration type. Next. Okay, so for methods, we firstly need to define something to understand our concept. We've defined concentration into two categories. The first one is effective concentration. So what does effective concentration mean? Well, we've defined effective concentration as the cognitive state of learning. So when you're learning something actually, then you are on an effective state of concentration. If not, you're concentrated on everything else, or you're just not concentrated, you're on ineffective concentration state. For more accuracy and to have a broadened view on all types of concentration, we've tested our users with 5 types of tests, from short memory to visual spatial, auditory, critical thinking, and linguistics. As you can see here, for the test, we've put the EEG on, we've calibrated it for 30 seconds, and then if we do an effective state test, we'd play them the test, and if it is ineffective, we let them stare at the black screen to give them ineffective concentration state. Next one, methodology. So for pre-processing, we firstly use the low-pass filter at the frequency of 1 Hertz to eliminate all the noise. After, we've notch filtered for the amplifier problem, like the DC at 50 Hertz. Next one, with high pass at 100 Hertz. Then we've used an independent component analysis, or more shortly, an ICA, to decompose our signals. Then we've used IC labeling for classification and more overly detect what type of signal is out there. Next one, we've reconstructed the signal based on the covariance matrix. And then we feature extracting using common spatial patterns. Next one, so after pre-processing, we've tried 4 methods of classifying the problem. So we've used the k-nearest neighbor algorithm, KNN, after support vector machines, SMV, next one decision trees and deep neural networks. I'm sorry. So after training, the system was implementing posing the educational materials, short visual and auditory stimuli, and also it was adjusted based on the concentration index. So basically on our machine, when you see educational videos, you don't just need to detect your concentration task, but you can also detect if you're concentrated, adding the factor of concentration index. Moreoverly, if you want, you can even adjust your environmental factors based on your concentration index. So if you don't have a big concentration index, it will start adjusting your environment parameters such as temperature, light, volume, etc. Next one is the results. Okay, so the biggest accuracy you've seen is the k-nearest neighbor with those an accuracy of 97 and 85%, so basically an 84% accuracy. The rest one you can see here have been overfitting because the data set was smaller, but with k-nearest neighbor and common spatial patterns, we've been able to obtain a big enough accuracy. Here you can see a small demo of our application. If the staff could play, please. Okay, so you can see here, we can log in our application where you can play an educational video. After starting, it will start detecting. As you can see here, it is not a concentration in effective state, and it starts pulsating, which means that it is an ineffective concentration state, and it is trying to offer the person visual and auditory stimuli for them to understand, to regain their focus. Now, furthermore, for this study, we've tested if offering them a virtual, augmented, or real world environment would affect their concentration state. And the short answer is yes, it does affect for a big margin. So for the augmented reality, for example, there was the biggest increase in the concentration index by a factor of 57%. Imagine that. So just by being on an augmented reality environment, you can have a 57 increase in your concentration. Moreoverly, this research is really interesting in my opinion because it has never been done before, and moreover it leaves room for not improvement but for more questions. For example, you might ask if the augmented reality is better, but why? Because for example our theory that is not yet proven states that it is better because it combines the both of them, and the cognitive state of the augmented reality can be perceived as a combination between real and virtual world environments. Okay, so thank you for your attention, and now discussion time.
Thank you very much. Quite interesting. So, any questions from audience? Otherwise, I will start firing tough questions. Okay. So, the first one, when you are doing signal processing.
Yes.
So the first one you're applying one hertz low pass filter, right?
Yes.
To take out the noise. And after that, you are taking 2 more steps. One is a notch
Filter, yes.
filter. At what frequency and why?
50 hertz because it is the amplifier that puts the DC.
Okay, so this is from the power supply.
Yes.
So the base noise of the power supply. And after that, you have a filter, I believe, 100 hertz.
Oh yes, a high pass filter.
Okay, so but you still have one hologram.
What? What?
EEG.
Yes.
So when you apply 100 hertz, right, you still have one-dimensional signal in time.
Yes, we still have one.
Okay. So how you're feeding this signal into your neural network model? Is it only one input, or you're breaking the signal?
So
you're having series of signals, and so basically how you're doing your
okay.
training exercise.
Okay, so the signal was epoched in 3 seconds. So as you have a 250 hertz sampling frequency, you divide it into epochs of 3 seconds, so 750 samples for one channel, so 60 channels would have the shape of the data of 60 and 750. Because IC labeling will classify the ICA signals in different types. So for example, one signal would be an eye blink, another one would be a brain signal, another one would be a heartbeat, and so you get the covariance matrix. So basically each channel, how much it is constructed from all of them. And so you reduce using Fourier transform the part of the signal from ICA that is not brain signal.
And my last question, can you explain a little bit that concentration index? How it's actually calculated and what is the meaning behind that that number?
Okay, so okay, so the concentration index is the power of the SMR band, which is between 12 and 15 hertz, plus the beta.
Power of the signal.
Is the yes.
Okay.
And basically this index measures how much concentration you are having at a moment. So basically beta is actually about critical thinking, and after you use the SMR band, which is the band for motor functions, you divide it by theta. Theta is the band for inactive thinking, like when you're half asleep, half awake.
Okay, so per my understanding, this is the power will equivalent to variance.
Yes.
Right? So it will show how signal is actually jumping up and up,
Yes.
and down. And so the more jumping, it's less concentration.
Yes.
And when you have high concentration, it's a less, that index will be kind of going to zero.
Yes.
Okay. Thank you very much.
Thank you.